On this episode of This Week in Space, we're talking about the Kepler Space Telescope and its mission to discover strange new worlds with Dr. Jason Steffen. Stay with us.
Podcasts you love.
From people you trust.
This is TWiS.
This is This Week in Space, episode number 137, recorded on November 15th, 2024. Strange New Worlds. Hello and welcome to another episode of This Week in Space, the Strange New Worlds edition. I'm Rod Pyle, Editor-in-Chief of Badaster Magazine, and I'm joined as always by the enterprising Tariq Malik, Editor-in-Chief of Space.com. Hello, brother. How are you?
I'm doing well. I feel like baby smooth. I shaved last night. I feel good. I feel young, Rod. I feel young.
I don't know, man. So it was just the few days growth you took off, right? Because you look like very different to me.
It was like a week.
Because normally, I mean, you have that kind of Father Goose sort of. I drank all the way till I could see the bottom of the bottle look, which I like on you. Yeah. Now you look like you're about 7.
I know. That's why I love it. It's such a nice reveal. Like after like we recorded our last episode, there was like a double the growth after that, and then it gets real. It's like that mangy. Like it looks awful and you can't keep it down kind of time.
Trim it.
I don't. I refuse. I don't need the beard anymore. So I get rid of it because it's all.
I encourage all my male friends to grow beards because it makes them look more intelligent. I'm working on Pascal now to try to spend a few days with him.
Very quickly. I grew a full beard in college, like way out to here. And the reason that I don't have a beard anymore is because I had spent my entire adolescent and early adult life fighting to have clear skin. I took medication for it and all of that. And I grew that beard out. And because I don't know how to care for beards,
I told you we were going to hear about his medical problems. Yeah. Okay.
No. Like when I broke out all over and I had ruined it. And it was like a whole another uphill thing to try to get my face clear again. And that was the last time I did it. So
what did you do about the hemorrhoids?
Oh my God.
Okay. So, gosh, moving on. We're here today to speak to Jason Steffen, Dr. Jason Steffen.
Doctor, yes.
Who has been a member of this Kepler Space Telescope team since 2008. Yeah. So he was there before they launched and is an assistant professor of physics at the University of Nevada, Las Vegas. And a nice guy, just wrote a book, looks like a really good one. So we can't wait to talk to him. But before we do, I'm charging you, audience. Don't forget to do us a solid. Make sure to like, subscribe, and do all the other podcast things to keep us alive and healthy and chunky in my case. All right. Let's go to a space joke from Joe Rich.
Joe!
This one popped up on our Discord. Hey, Tariq.
Yes, Rod.
Why did the star break up with the black hole?
I don't know why.
Because it felt like it was getting sucked into a toxic relationship.
Oh, funny, Joe. Black holes don't suck, they attract, right?
That's a very interesting point.
Right?
See, this is why everybody loves you, because you can put a good face on everything and I can tear anything down. Now, I've heard that some folks want to jump in the nearest wormhole when it's time for the space joke on this show, but you can help. And I want you to listen because it's been down lately. Send us your best, worst, or most indifferent space joke. Now, we really like the ones that aren't taken from the internet because we've already used all those. If you get something good out of AI, that's okay. But just the stuff on, Bennett Cerf's 101 best space jokes or something, I hear they got a restaurant on the moon, but it has no atmosphere. We've done those in almost 140 episodes. So we need good ones. All right. And now, wait a minute. I hear something. I believe it's time for headlines.
Headline news.
My mother would be so proud.
Yeah.
Because I engineered that all by myself. Well,
I love it.
All right. So first headline, and love your title here. So, who walks among us?
I think that's your title, Rod.
Oh, was that mine? Okay. Well, tell us a story, Uncle Tariq.
Well, it may come as a surprise to you all that this week, the House of Representatives Committee on Oversight and Accountability welcomed, I guess, the true believers, right? They had a hearing called, and I quote, "the unidentified anomalous phenomena Exposing the Truth. That was the name of it. That's the name of their meeting. But they had all
seriously. I mean, they put that on the docket as
that's the name of it. That's the name of the meeting. Exposing the Truth. Right.
Kill me now. Okay.
But they had a bunch of experts and I guess witness folks.
Now, wait, were these experts or experts air quotes for the people not watching the video?
I mean, I think that it's really, for the listener and the viewer and the reader to decide, right? It's yet another congressional UFO hearing, and I'm going to say that again, congressional. That means that your tax dollars are paying for this meeting about people saying that there are UFOs. Now, I think that there's life out there somewhere, but I don't think that they're buzzing us for joyrides, right? I don't think that they're doing that. And yet,
there's a recent paper out that would contradict you. All kinds of evidence about, we know from big names.
I just think that ET has better things to do. But I digress. That's not the point of this story. This story is just a note that they really did take in like a bunch of new testimony from some folks. I mean, you've got
it's some well-positioned folks of some stature.
A former U.S. counterintelligence officer, a retired U.S. Navy rear admiral, a former NASA associate administrator. All these people were there.
So that was Mike Gold, right?
Yeah, it was Mike Gold. That's right.
Yeah,
he was
so
there
it's not. This isn't the deputy administrator number 2. This is next level down, associate administrator, and there's a number of those, right?
Exactly. Yeah. And so they were there to make the case to say that we are not alone in the cosmos. That's what one of them said. They said that excessive secrecy has led to grave misdeeds against loyal civil servants, military personnel, and the public to hide the fact that we are not alone. So they're claiming cover up, right? Some of them are. Not all of them, but some of them are.
It wouldn't be outside the realm of possibilities. There's been plenty covered up over the years, as we found out later. But, I'm not Mike Gold, who's a brilliant guy, associate administrator, or some of the others. There's some wackadoodles in this field, but there's a lot of really smart people. I mean, you don't become a rear admiral by being a gumball brain. I just don't understand. And, maybe this is my naivete, how these advanced, races that can cross thousands of light years, presumably either by folding space and walking in through my closet or by coming in a spaceship, why they keep crashing into our planet once they get here, or if they're coming down to look at a carrier battle group. We can almost make planes that are invisible. Why can't they?
Yeah, you would think so. You would think so. So, well, I guess that the whole point is that it seems like these experts, as well as some members of Congress, say that they want the government to be more transparent, like nothing should be hidden. In fact, Representative Nancy Mace of South Carolina said that she was disturbed by the lack of transparency, even that the budgets are being hidden for the people that are looking at a lot of this stuff. So they want to know just more about what's going on and get everything just up and out there. So I don't know. Are you ready? Are you ready to face our alien overlords, Rod? No?
I feel like I've been facing something worse than that for 2 years, Tariq.
Well, we'll see.
Okay. So I love this one. Is SLS a dead rocket walking? That's definitely your headline.
Oh, yeah. I wrote that.
This has been talked about and talked about and talked about in the space community. Yeah. Less so, as far as I'm aware, in government circles. But there's a new, I hear tell as of last Tuesday, there's a new sheriff coming to town. And actually, I spent this last conference I was at last week sitting next to the gentleman who may very well be the next NASA administrator. Mm-hmm. And I think if that's the case, SLS may not clear the hurdle.
So this is really interesting. And I put this on here. This came from, so the other story, the alien one, came from space.com, but everyone else and their mother picked up that story. I heard it on NPR last night. This one actually is interesting because it kind of has two different sources. Number one is our good friend Eric Berger, who was on the show last episode talking about his new book, as well as SpaceX and Starship. By the way, we didn't hint about it, but Starship might launch on November 18th, a few days from now. That'll be really exciting. We'll talk about it next episode. But Eric tweeted out, anyway, he posted a note this week where he said that he has heard from conversations from the experts that he has had, all the experts that tell him things, that he's seeing a lot of signs that the SLS days are numbered, that it's not It's not 100%. Nothing is final yet, but the
Right.
conversations are seriously trending into that in that direction. And futurism picked up on that because Eric is not a spring chicken. Eric knows things. We heard all about his expertise on the last episode, and they really dived into this. And the reason I brought this up is because it isn't new, like you just said, Rod. In fact, there was an op-ed in the Washington Post that said that the SLS really should be canceled to make way for something that's more efficient, that's faster, that's cheaper, $4 billion a year for maybe one launch, right? Not kind of the cadence that we were hoping for. So, it's just something that we should be thinking about. This was NASA's biggest rocket since the Saturn V. It's launched once. It's supposedly going to launch again next year, but it's way behind schedule. Technically, we kind of should have been landing on the moon by now. We're not there, and it's very close to potentially just fading away. A lot like Ares 1X, a lot like Ares 5.
Well, except
from Constellation.
The money spent and the metal bent, the time and effort spent. I mean, there's multiple cores. There's a lot of pieces hanging around. There's all this development, new engines being designed and possibly built. I don't know if they started on the new batch of RS-25s or not. So you've got all this potential huge waste on a scale that doesn't quite approach the F-35, but it's still wasteful. On the other hand, you've got the new government efficiency expert maybe coming in, Elon Musk himself.
Oh, yeah, that's new too, by the way.
But there's also been an awful lot of planning and people, developing pretty convincing plans about how you could achieve at least the interim moon results you want, which is getting there and kind of setting up basic infrastructure, not the whole big thing necessarily. Just using the Falcon Heavy and possibly the New Glenn. You just have to launch it in pieces. That's been studied since the 50s.
And I think that's the big thing. We have a new administration coming in, a new president who made it very clear in the end of their administration that they wanted to get to the moon as how did Mike Pence put it? By any means necessary, and
meaning Boeing, no more cost plus for you.
So it is not out of the realm of possibility that viewpoint, that discussion will come up. And as you mentioned, Elon Musk was officially appointed, co-lead along with Vivek Ramaswamy of this Department of Government Efficiency. There's going to be a lot of focus on getting that stuff done quickly. So.
Bye Social Security. Okay, because think of what you could spend that money on instead of supporting old farts like me, although I'm not taking it yet. Okay, so we got to move along because we're burning time here. But
yes.
So, Tariq.
Yes.
Headlines. Really? Did we kill life on Mars? Now, I understand.
Did we?
Well, having read the story, I understand what you're getting at, but you, of course, know. I mean, it's funny, when you're writing these headlines or subheads like I do for my books, sometimes it takes somebody else tapping you on the shoulder saying, that sounds like X, right? This one struck me as, did the Viking landing manage to kill everything on Mars that might have been? But what you're really saying is, did it kill the little bit of dirt that was dumped into the life science experiment?
That's right. I will fall on the sword for this one because I'm fairly certain that's what I think I had a direct input into that headline there.
So basically, you were intending what I said the first time, right?
Yeah. Well, yeah, I tell you. No, but this is funny because this is actually, it's not something, I think a lot of our listeners in the know, this won't be like a surprising kind of take for them about there's been discussions about the life-seeking experiment on the Viking landers for a long time and about what did they really detect, etc. But this week in Nature Astronomy, there was a new study that came out, or perhaps it's like a commentary that they published. This the astrobiologist Dirk Schultz, I hope I pronounced this right, Makuch, at the Technische Universität Berlin in Germany.
Wow, mangled that.
I'm sure I did. I'm so sorry, Dirk, but man, Dirk is an awesome name.
Isn't it?
Yeah.
Like being rock strong or something.
That's right. So he has brought back the hypothesis that the Viking landers may have indeed had like evidence of microbial life in the palm of their proverbial scoop. But because their detection experiment for this used water, right, just to as part of the process, that water was enough to kill the extremely anaerobic, is that right? And no, the really dry life that could have been there. That this life, according to this commentary, was even drier than what we see in places like the Atacama Desert, where microbes get their water from salts that get their moisture from the atmosphere. But even like a tiny drop of water would be enough. It's like being drowned. Basically, it's enough to kill those microbes. And that because we use that on the Viking landers, and not knowing the sensitivity of these potential microbes, that it was enough to kill them. And then when we look at it, we just see a bunch of dead dirt, and we're like, well, that's it. Has been planet. We don't need to go there. So,
and to be specific, so when you say look at it, I mean all we were looking at was the gas release from whatever happened.
Exactly.
So just to back up a step, Viking would scoop up some soil, it would drop it in one of 3 funnels on top of the lander deck, and then in one, I think all 3. I'd have to go back and look. I think all 3 used water, but 1 or 2 of them actually had a nutrient broth as well, which also might have been toxic, these little critters, because we're just guessing. This is the 60s, and they were really basing this on life science info from the 50s, because it was the 70s at launch, but it was 60s it was being developed. And we didn't know a whole lot at that point compared to now. We didn't know about extreme files. We didn't know about some of these weird life forms, how they live under the crust of rocks and oceanic vents and all that. It was kind of like, hey, if I have a box of kittens and I feed them some baked chicken, they'll be okay and they'll pass gas and we can measure the gas. And that's basically what Viking was doing. But once I read the article, which I thought was a really good article, so congrats on that, despite the title, it was pretty compelling. And I look forward to reading his paper about, look, this stuff has been living on this dry, essentially dead, windswept, waterless planet. Of course it's going to go, you're killing me if you dump a bunch of water on it. So
burns.
It kind of makes sense. Yeah, right.
They found like the microbial version of the Wicked Witch of the West, right? So on Mars. So. Okay,
pick one of the remaining 2 stories, and then we'll jump into our interview.
No, I know we got to go quickly because we've got a long way to go. But there was such an interesting little note about Voyager 2, and this actually came up in our chat from our Discord followers too, who reminded us that Uranus. This is from Life Science. This is from Life Science because I love their headline that we've been wrong about Uranus for nearly 40 years. But the scientists dove back into the Voyager 2 data, and they found that Uranus or Uranus, depending on how you like to pronounce it, might have actually been undergoing a bit of an event when Voyager 2 went there. So that what we saw in the imagery, in the data that was collected, was like that it was actually something really weird and outspoken because of ongoing solar events and whatnot. Basically, that it was being affected, by this space weather event, and I believe that it was like the magnetosphere that was messing it all up. From a plasma burst from the sun.
Was the idea that the effect was why we saw the winds moving so quickly, or which part of the observations?
Well, it was about it's like magnet. Oh my gosh, this is. I should have read it more. No, but the idea is that it messed up the magnetic field because it's this plasma burst from the sun, right? So it hits the magnetic field and it buffers it. That's how we get the northern lights. It's how we get a lot of communication stuff on Earth. But that it messed it up, right? Because the solar wind was just really blowing it out of shape, and then Voyager 2 comes by and is like, well, I'm going to measure the magnetic sphere here. And this is a really weird planet. It looks like it's all lopsided. And then we are like, wow, we've never been here before, but I guess this is what it's like all the time. And then we zoom on by off out of the solar system. So it's just really, it was in the November 11th edition of Nature Astronomy. It's just fun to know that data is still, like they're finding new things in it, and that maybe the magnetic field, shape and concepts that we thought of this lopsided planet, that it really isn't like that. We're not going to really know, unless we go back up close again to Uranus.
So
Rod. up close to.
Okay. I'm got
It took me. I've been
going there. So this is kind of
for a long time.
This is kind of like
Theo!
you stay away from that part of me. So it's kind of like, to draw a really stupid analogy, going on the morning of January 2nd, driving through my hometown of Pasadena and thinking, gee, the streets must be waist deep in trash all the time because it's the day after the Rose Parade.
Exactly.
That town is a wreck. Did you ever go to the Rose Parade when you lived out here?
I marched in the Rose Parade as a member of the USC marching band. I'll have you not.
Semi-professional dweeb. That's right.
Oh my gosh! That was my freshman year in college, and we won the Rose Bowl under John Robinson, who passed away this week. Our coach,
we did
by
it
the way.
in high school, but that's okay. We can't all be early achievers. But yeah, the next day, man, that town looks like Dresden in 1944 or something. All right, let's have a show.
Yes, let's do it.
Okay, let's move on. We're going to jump to an ad real quick, and we'll be right back with Jason Steffen. Welcome back, everyone, and welcome, Jason. It's so good to see you here. Thanks for joining us today. I appreciate it.
Thanks for having me. It's my pleasure.
And more importantly, congratulations on not just the book, but a book, because doing any book these days is such a challenge that it's rarefied air for people that get something published, and you've done well, so congratulations.
Yes, you're here.
So we have you here specifically because you've been a member of the Kepler Space Telescope science team basically since the beginning, since before launch. But can you give us a little bit of background on who Jason Steffen is and how you got to where you are today?
So I was born in California, and then peace broke out in the world when the Vietnam War ended, and grew up in Utah. So when I was 3 months old, grew up in Utah, went to the local college, but eventually went to the University of Washington to graduate school. That's where I met my advisor, who was the greatest PhD advisor ever to walk the face of the earth. He got me started on a practice problem, and that practice problem eventually, I was supposed to be doing what is the image of a black hole going to look like when we get very long baseline interferometry. So the pictures of the black hole that came out a few years ago, that was supposed to be me. But I wasn't quite ready for that yet. I hadn't had the classes that would have been useful. And so he's like, well, there's this practice problem that should only take us a few months to put together, and then we can go back to this. That practice problem turned out to be looking at the gravitational effects of multiple planets in a planetary system and how those would translate into what we observe in the orbital periods that we measure. So how the orbital periods change as the planets interact with each other. So that practice problem turned out to be really interesting, and it turned into a dissertation. And eventually NASA, when the Kepler mission was about to launch, basically said, we're looking for people who look for gravitational interactions within planetary systems to see the changes in the orbital periods. And I raised my hand and said, I can do that. And that's how I pulled the wool over everybody's eyes and was brought onto the Kepler team.
Boy, that's one of the best ramp up answers I've heard in a long time. Thank you.
Who was your advisor? Because you said he was the best of all time. Who, just to give a shout out for folks, for inspiration.
So his name's Eric Agol. He is at the University of Washington. He has a twin brother who's a mathematician at Berkeley who solved some long-standing question and won $1 million prize for.
Wow.
So it's like there was too much intelligence to put in one body, so they bifurcated in the womb, and so I
think I saw that movie.
Yeah, it's twins, except it wasn't as asymmetric as the Danny DeVito one.
Right.
I love that we're like 5 minutes in and we're dropping like 1990s comedy film drops. I think that's hilarious.
That's when all the good movies ended, was in the 80s and 90s. So,
that's right. Well, I'll follow up, Jason, with my traditional question is about how you got into space overall, because clearly
come on, say it the way you always say.
Well, I will, but you have to let me get my build up there. But you clearly you had an interest when you got into school to start studying everything. But I'm curious about little Jason, like how did the space bug get you? What were you? Was it something that had grabbed you when you were young? Was it something that you actually found when you were in college? How did the space bug bite you?
So I guess it's a little bit of both. My father was an Air Force pilot. And so my brother really was into the military. And he bought this book it was called Wings, I think. And it just showed, it was Modern Military Aircraft was the name of the book. And it showed like pictures of all the airplanes that every country in the world had. So I had SR-71 and the F-16 and so this was when I was in elementary school. And so I would, with my friends, design fighter planes. Of course, this is also when Top Gun came out. So Top Gun was on the air, was in the movie theaters and so aerospace was a big deal. Also the space shuttle program was kind of in full swing in the mid 80s. So all the movies were good. The music was good. The space shuttle was there. Top Gun was there. The United States was winning at everything. And so my friends and I, we would always draw like new fighter jets and say how fast they could go and give the statistics and stuff like that. So I was going to be an aerospace engineer when I went to college, except that where I went to college, they didn't have aerospace engineering. So I did have an astronomy class my first quarter at Weber State University in Ogden, Utah, which is multi-year running the national cheer champion. So they're not, their other athletic programs aren't quite as reputable as that. But so I went there and I had an astronomy class my first quarter, read the whole book before class even started. And that was kind of the beginning of the end for my aerospace engineering career and got me into space and astronomy.
There is a universe now where you and I are like super high aerospace engineer like partners doing something, because
no, there's not.
I was going to do the same thing. I was going to study journalism and aerospace engineering at USC, and they told me when I went there to register for classes that I couldn't do both at the same time. I'd have to pick one, and so I ended up picking.
That's the worst, because I was a physics and history major for a period of time, but because they were in two different colleges, it wouldn't have worked out. So, and it was a lot of reading.
So Tariq, I think the universe in which you're an aerospace engineer and writer is probably the universe in which Jason is God. Because we got to keep these separations, in place. And in that universe, I'm a dog catcher. So, all right. So
that would have been the one similar to the one when I was a garbage man, because that looked like the coolest job ever when I was growing up. You get to ride on the side of the truck and everything.
Yeah, I thought firemen riding on the back of the truck had more fun, but then I actually bought a fire truck about 25 years ago.
You did not.
I had a little kid. I did. I had a 26-foot pumper, and once had somebody else drive it while I stood on the back, and it was terrifying. So you can see why they took those little steps up. But I digress. I'll talk about the fire truck another day.
We got to talk about that sometime soon.
Yeah, it was definitely an outlier experience.
All the careers I could have had, right?
Yeah, exactly. Well, there are probably a lot more possibilities for you than there were for me, at least successful ones. But speaking of successes, can you tell us, just kind of give us the box top version of what Kepler was and what led up to Kepler becoming a valid mission?
So Kepler was, it was originally conceived in the 1980s. So when all the good stuff was happening, the William Barucki, started piecing together what the Kepler mission would be. And it was, the goal was to measure the frequency of Earth-sized planets in Earth-like orbits, orbiting sun-like stars. So how common is the Earth? Are we alone? Are we the only Earth that there could be in the solar system or in the universe? Or are there many of them? So the way that it measures the presence of planets is it monitors the brightness of the stars over time. And if a planet happens to pass in front of the star, so if the planet transits the star, then the star gets a little bit dimmer. And so it looks for these small changes in the brightness of the star as the planets transit. In order to do that, it has to monitor simultaneously about 150,000 stars, just because the geometric alignment of the planetary orbit is pretty small. It's relatively low probability. And the probability of an individual transit, for example, for the Earth would only be about 12 hours every year. And so you have to have a lot of things, because if you miss one transit, then you miss it, right? You have to wait for another year for something else to come along. So you want to get a fairly sizable sample of target stars. So it monitored about 150,000 stars, looking for the changes in brightness. That would be the equivalent of looking down at Las Vegas from space and identifying individual flies as they buzz around the streetlights.
Oh man,
That is a great metaphor. So in a sense, it's a giant spaceborne photometer.
Yeah, it's a photometer, so it doesn't take pretty images. In that it's not designed to take high detailed images that show lots of structure and things like that. It's just designed to count photons. Just to give an idea, so the Kepler field of view is this thing that I have in the background here. That footprint on the sky is roughly the same size as the palm of your hand if your arm is extended. Where if you compare that to the wide field camera on the Hubble Space Telescope, that would fit inside the eye of Abraham Lincoln for a penny that's held at arm's length. So
wow, these comparisons are like, I mean, you should write a book. Oh wait, you did. But these are like the big golden book of analogies for the Kepler Space Telescope. I'm going to jump in here for a second. I'm going to take a break, and then we'll come back. And please feel free to finish your answer as you wish, and then Tariq will have his shot. Stand by. We'll be right back. All right. So please go ahead. I'm sorry I jumped in there.
Okay.
Oh, well, I guess I'll ask real quick then about, you kind of touched on how, you kind of got roped in, I would say that, with air quotes, into the Kepler mission when they were
fell
looking
backwards into it.
or they were looking for someone with a particular set of skills as they would say, and then you met that. I'm curious how you got onto the team. And I think one of the things that, and if I missed it, I apologize. The stars that you were looking at with Kepler, that's toward the constellation Cygnus, right? For people that
it's between Cygnus. It's between Cygnus and Lyra. So Cygnus is in the plane of the Milky Way galaxy. One of the challenges, if you have too many stars in the field, because Kepler's a photometer and not an imager, you run into a confusion limit where there's so many stars that land on the same pixels that you can't separate them anymore. Mm-hmm. So you can't point it in the plane of the galaxy. But if you point it too far away from the plane of the galaxy, then there aren't enough stars to do your survey. So you have to kind of there's a sweet spot above the plane of the galaxy, which in this case happened to lie between Cygnus and Lyra so it's up in the summer sky.
Yeah, I wanted to make sure that there are some folks that might want to look up and reminisce, and so where they should be looking. But what was that phone call like when NASA came calling, or the Kepler team came calling to you? I mean, was it something that you were already trying to get involved in? Was it something that happened serendipitously, or how did you become part of the actual team at that point when they needed you?
So when you have a NASA mission, the expertise that it takes to build the mission is different than the expertise it takes to run the mission and analyze the data. So you don't necessarily want someone like me fiddling around with the telescope or the hardware. And so what happens is once a mission gets selected, they'll have it being developed for a period of time. And then right before its launch, NASA will send out a solicitation, an invitation basically to join the team. So you have to write a proposal that says, here's what I'm going to do for this mission. So those are called participating scientists. So they're generally full members of the team in that they have voting rights and that kind of stuff. But they're brought on at the late stages in order to do the analysis of the data that comes out to kind of expand the scientific footprint of the mission. And so NASA in late 2007, I think it was then, announced that they were bringing on participating scientists, and they listed a few of the things that they were looking for. And it just so happened that they almost exactly copied my dissertation title into that. And so then it's just a matter of writing a proposal and then saying, here's what I would do if I were selected. And then a few months later, I got the message, congratulations, you're selected.
Oh, that's great. That's great. And can I ask, because some of our listeners might know like different ways to find, I guess, signs of planets around stars. There's like the I guess the wobble method, right? The gravitational perturbations from it.
Radial velocity, I think.
Yeah. and then this dimming kind of effects too. So I'm curious what made the Kepler method really stand out for what the telescope was designed to you and the team to kind of look for these signs of planets as opposed to other methods to find them.
Yeah, so the two workhorse methods for finding planets, especially 20 years ago when this was all coming to fruition, were the Doppler measurement, so that the wobble or radial velocity, So that you're looking at the Doppler shift of the star because of the planet orbiting around the star. And then the transit method, which is you monitor a bunch of stars and look for changes in the brightness. These were actually both proposed in the 1950s by Otto Struve. He said, our spectrographs are getting good enough where we might be able to see a Jupiter-mass planet on a one-day orbit. Not that anyone would ever expect that there would be a Jupiter-mass planet on a one-day orbit. But his reasoning was that we see stars that are that close, and so maybe we'll see planets that are that close. And then he also said that we might be able to measure the changing in the brightness with photometric surveys. And so for a couple of decades, those two methods were just kind of stewing in the background. And the Doppler shift measurements, those ones kind of came to fruition first in the mid 90s. But really, the advent of the, so this was 1956 when that first paper came out. The CCD camera was invented in 1969. And so that was kind of ripe for exploitation, as was a lot of computing development. So it's a lot easier to do an analysis of a single star with a spectrograph than it is to analyze. I should say it takes less computing power to analyze the spectrum of a star than it does to analyze a full frame image of the Kepler field of view. Actually, 60,000 full frame images of the Kepler field of view or something like that. And so it was kind of a confluence of the analysis technology, the computational power, and the instruments that brought both of them together. So with the Doppler shift measurement, you really need big pieces of glass with expensive spectrographs in order to make high precision measurements. And so, you're looking at $10 million to build a spectrograph, which granted is less than $1 billion to fly a space mission. But the two different techniques actually measure two different properties. So the Doppler shift measurements, you only get the mass of the planet. You don't get the planet size. With the transit measurements, you get the planet size, but you don't get the planet mass. And so by doing both of them together, you can get both the size and the mass, which helps with understanding, what are they made out of? Where might they have formed? How would the system have evolved after they formed? Things like that.
So this is a wonderful answer, because I was reading about that yesterday, trying to piece together what you just said in simple terms like that in my little Labrador brain, and it wasn't working. So let me just jump back here. The Kepler launched in 2009, and it's a 37-inch optic in there, mirror. One of the things I found fascinating about it is that you keep within the optical train, you keep it deliberately, I guess, defocused, you'd say, so that you don't end up frying or oversaturating your CCDs with individual hot pixels from the stars, right?
So one thing that I learned as I was researching this book, it had been proposed that we defocus the images, but it turns out that they found that they got better results if they really had good focusing. But the reason that defocusing was proposed is because you're only looking for a change of like 20 parts per million in the brightness of the stars. So you don't have a lot of wiggle room for things like temperature variations or sensitivity variations. So each individual pixel in the camera has slight sensitivity variations across the surface. And so if the camera isn't pointed exactly at the same spot and the image drifts across the different pixels, then you can actually get fluctuations in brightness that are comparable to what you would see with a planet, but it's just because of poor pointing. And so the idea was that if you defocus the camera, it's already spread across a lot of pixels, and then you average it out. But it turns out we got slightly better performance if we had a good focus and just focus and worried more about keeping the pointing stable, which is actually ultimately what led to the demise of the mission, because keeping the pointing stable uses the reaction wheels, and they had only one spare, and two of the reaction wheels broke. So the mission came to, it wasn't necessarily an early demise, because it did last for about 6 months longer than the warranty.
Right.
But when those two reaction wheels failed, it could no longer point as stably as was needed to get the kind of data that Kepler had been getting. And so they had to repurpose the spacecraft.
Don't tell us more, because this is our big surprise unveiling for the next chunk of the show. But I will say, you guys did what to lay people like me was a heroic Hail Mary to keep this thing going. So we're going to jump to one more ad and we'll be right back. Stand by. All right, good. Nobody repositioned their telescope. Everybody's still here. We're good to go. So before we get into K2, could you talk a little bit about, well, two things, I guess, and then I'll toss over to Tariq. But I don't think a lot of people realize that to do the first of the two methods, the photometry method, we have to assume that a certain number of planets in the direction you're looking are in the same equatorial plane as we're looking, right? Because if they're going around the star top to bottom, we're not going to see anything. They have to pass in between us and that star, so that eliminates some of them. So you have, in this field of view, you had a lot of target opportunities, but what are the odds you're going to find what you want?
Yeah, so for the Earth transiting the sun from a random point, it's only about 1% of observers that will see the Earth passing in front of the sun. And so you see 100,000 stars, and you would expect that something on the order of 1% of them, if all of the stars have planets, then you get something on the order of 1% of them. And that's roughly what we saw. Actually, we saw slightly more than that. So we surveyed, in the end, about 200,000 stars, and we saw signals for about 5,000 or so planets. 5,000 planets. But a lot of those planets are in multi-planet systems. And so it really was right around 1% of the stars that happened to have a fortuitous alignment. The result of that is that it implies that basically at least 30 to 50% of all stars have planetary systems like the ones that Kepler saw, which is interesting because Kepler was just barely sensitive to Earth. And so it's entirely possible that the other 50 to 60% of stars in the sky have planetary systems that are more like the solar system. So the solar system was really on the edge of what Kepler would be able to find. And there are probably planetary systems similar to the solar system that Kepler didn't see simply because the star happened to be a little bit more noisy, or there was a gap in the data, or just when they did some of the noise mitigation, it happened to remove the signal from the planet. And so the jury is still out in terms of how common solar system like planetary systems there are, where the rocky planets are relatively far out and the gas giants are even farther out. When I say relatively far out, is that it's because the Kepler planetary systems, the ones that it found most often, had orbital periods that were only like 2 or 3 weeks long. So the typical planets are orbiting well inside the orbit of Venus or Mercury. So it's a different kind of animal compared to the solar system. The solar system has planets on month and year-long orbits and decade-long orbits, where most Kepler planetary systems are on week-long orbits or month-long orbits.
Yeah, I wanted to follow up, I guess, with that, because you mentioned 5,000 planets, indicated by Kepler overall about those sum results. So we had, and I think Rod wants to ask about the post, primary mission bit there. So your primary mission, I think it was planned for 3.5 years or so.
Yeah, planned for 3.5 and went for 4.
You went for 4, and then you mentioned that you find the signs of these 5,000 planets there. I mean, is that like the good number that came from that, or was that total from later on? And then was the next step when Kepler found these hints, these light signal changes indicating planets, they were followed up on, right, to confirm them by other means? Is that kind of what the process was like for folks beyond Kepler 2?
Yeah, so it basically found a bunch of what are called threshold crossing events, which is changes in brightness that match, that are large enough that they deserve some attention. And there were tens of thousands of threshold crossing events. Initially, those were gone through one at a time by people in order to weed out, spurious signals, cosmic rays, and things like that. And then we narrowed it down to a candidate list. And then the candidate list was sent out to a bunch of astronomers called the Kepler Follow-Up Program, the KFOP. And they used...
Sounds like a pop group.
Yeah. So they used like every piece of glass at their means, at their disposal, to look for, what are the properties of the star that it's orbiting? What are the like the detailed properties. We had some indication of what the stars were similar to the sun, but in terms of like what's their chemical composition and things like that, that was new. That was information that we didn't have. So they followed up to get reconnaissance spectroscopy to see maybe there's a multi-star system here. Do we see a signature of 2 stars or multiple stars? And then starting to rule out if there's a blend scenario where you might have a foreground star with a background eclipsing binary that would mimic a signal. So there was a lot of detective work that had to go in after that. And then, so one of the issues that we faced early on in the mission was that the rate of planet discoveries from this mission was really quite slow. It took, so we first, the first announcements we made was about 5 planets. And that was about 6 months after we got data back from the spacecraft. And then a year later, we still had 5 planets. And that was partly because we were just, how do you grapple? It's hard to swallow when you're drinking from the fire hose. And so how do you grapple with all of this information? But even then, the systems were trickling out. We had a bunch of really interesting systems that came out early on. And the really interesting systems would require a disproportionate amount of analysis in order to kind of flesh them out. So we found some museum pieces. So this would be like the first rocky planet on Kepler 10, the first planet that showed dynamical interactions within the system, like Kepler 9, the first planetary system that had many transiting planets, with like Kepler 11, or the first circumbinary planet that was Kepler 16. So a lot of the early ones took, a disproportionate amount of resources to do the studies on them. But then, after about a year and change, the mission there was a pressure, we got to get the catalog list longer than 10. And so myself and a group of my collaborators developed some faster methods to confirm planets. So that got us from about, say, 1 dozen to 50 or 60 planets. So that was kind of a big breakthrough. And then there were it took a few years to develop the statistics, like the statistical properties that we were looking for, in order to say, okay, the probability of these planets being real is, some high number. Once those tools were developed, then we started finding planets confirming planets by the thousands. So I guess there's an important, in the life of a threshold crossing event. So your threshold crossing event, a human says, oh, good boy, you look like a planet. And so then you're moved to a Kepler object of interest. And then you get reconnaissance spectroscopy that shows that you're not an eclipsing binary or something like that. So then you're moved on to the planet candidate list. And most of the discoveries from Kepler are still on the planet candidate list. Then it's some types of analyses can verify that you're an actual planet to within the acceptable confidence level. And so then you go from a planet candidate to an actual planet. We even had 2 different terms for this process. You could either be validated, meaning that
Like
people
parking.
accepted you for who you were. No, so validated would be that we ruled out a substantial number of false positive things, or you could be confirmed. Confirmed would mean that you had, for a given planet, you had a signal, some kind of dynamical signal that demonstrated that you were planetary mass. So if you followed up a given planet candidate with Doppler shift measurements and found that you were actually a planet, then you'd be confirmed. If you looked at a system and said, well, the chances of this being a false positive are less than 0.01%, then you'd be validated. I mean, it's kind of a technical issue, but it was something that I guess we felt very careful. We wanted to be careful in our terminology.
That sounds like something that astronomers will fight over at the bar, right?
Oh yeah, like the habitable zone.
Their candidates.
So,
Well-
Tariq, I think we've been doing this show for the last 2 years. Have you been waiting for validation or confirmation? Because I'm looking for both.
I'm waiting. I get confirmation from my scale that I'm planet mass every morning, Rod. So,
Oh, yeah. Okay, Anthony's pinging me. He wants another commercial. These guys are merciless. So let's take a quick ad break here, and we'll be back with more fun. Stand by. So one of the things that I read about this mission was that you had, what will we call it, a richness of data that became kind of a problem because this thing was collecting so much data. And I guess it stored it on board and did some parsing there, but it was still sending back gigabytes of stuff that you guys had to sort through. And then the real work begins on the ground, right? Is that?
Yeah. In fact, so with each new data that was brought down, you have to reanalyze it from scratch, because if you take 3 months of data, but the planet that you happen to see in that region has a 6-month orbital period, then you kind of have to start over. So you get new data down, and then you reanalyze from the beginning to the end of the time series. And then you get 3 more months of data, and then you reanalyze it. And then you get 3 more months of data, and you reanalyze it. And it was getting to the point where it was taking longer to analyze the data than the time interval between successive data downlinks. And that was a problem. And so, I mean, a number of things that you discover again and again and again. For example, early in the mission, it was faster to transport the data from one computer to another by saving it to a hard drive and then walking the hard drive over to the other computer and plugging it in. Because, you're talking about gigabytes, and going through the internet at the time was pretty slow. And so, it's still true today that the fastest way to get astronomical data from one place to another, is to put it on magnetic tape and then fly it from one place to another. So,
aren't you glad you aren't using punch cards?
Yeah, those were the days.
Yeah.
So that was one issue that we ran into. Also, you have to have enough warm bodies to make sure everything is functioning correctly. So there was some staffing that had to take place in the science office. Of course, launch always gets delayed, and there's always last minute changes. And so that requires that the software engineers focus on writing the software that flies the spacecraft instead of writing the software that analyzes the data that's going to come from the spacecraft. And so, resources were allocated towards launch that ultimately, in principle, would have gone towards the data analysis pipeline. So in the end, after about 6 to 8 months or so, all of the data analysis was moved to the Pleiades supercomputer, which is a supercomputer that's about the size of a grocery store, just lined with lots of processors. And then there they had enough computing power to kind of churn through it. But there was, even issues. There was a lot of politics that came into play. It's not partisan politics, but just, so JPL, for example, the Jet Propulsion Laboratory in Pasadena, is older than NASA. And so it was grandfathered in under different rules than the other NASA centers. And so the mission was run out of NASA Ames, but NASA Ames, because it has a different set of rules, they were really worried that certain bits of data might fall into the wrong hands, and then so we can't export the data to get it analyzed by something. And so there had to be some negotiation to take the data and put it on the JPL website, because JPL has different rules that allow us to get, so there were a bunch of these things that had to get shaken out in the first year of the mission, including, just the fact that we're drinking from the fire hose every time something came down. Well, and there were a bunch of artifacts also. So for example, occasionally the whole camera would get bright. So you'd have this, you'd be looking at something, and then the whole camera lights up, and then it calms back down again. And no one was sure what it was. There was a Ball engineer, his last name was Argabright, and he identified them. And so they called them Argabrightening events.
Wow.
And what we think it was is that you have micrometeorites out in space. It's kind of a harsh environment, and it would chip off pieces of paint, and then they would drift across the telescope aperture and reflect light from the sun into the telescope. So you have a little paint fleck that is reflecting sunlight into the telescope and causing it to get brighter than the signal that we were looking for. And so, you have to, once you see them and you see kind of what are the characteristics of these events, how do you treat them? How do you remove them from the data? So the analysis pipeline had to constantly be developed. Eventually, by the time the mission ended, the Kepler mission ended, but the analysis of the data persisted for about 5 more years. Mm-hmm. So the final Kepler catalog of actual real Kepler data, not the subsequent data, that came out in 2018. And that was the first time that it was completely automated from the start to the end. And the advantage of having something automated is that computers don't get bored the same way that graduate students do. And so, And so when you're analyzing the threshold crossing events and things like that, it's better to be consistent than it is to be. It's better to be consistent than it is to be thorough.
Right.
It's better to know what your systematics are rather than really scrutinize something and pay a heterogeneous amount of attention from one object to the next.
Oh, he's using college words on us here.
Well,
Tariq, clear the room.
I just want to say really quickly, Rod. But Jason, you hit the nail on the head. As a graduate student who was tentatively given access to astronomy data, I promptly got bored and accidentally erased a week's worth of observations. So very, very poignant observation.
We've all been there. So RM-RF star. That was a mistake that everybody's made at one point or other.
Sorry, go ahead.
Not me, because they never let me close to that stuff. I just wanted to add a fun fact here. One of the reasons that Mariner 4 got lost on its way to Mars was also paint flecks and dust, because it had a cloud of detritus sort of surrounding it from when it, because it was like, I don't know, fourth or fifth planetary or space probe we had sent out of that type. And when the fairing came loose and the rocket continued going, they let Mariner go, all this crud that was, I guess, sealed up with it just started drifting along with it. So every time the Canopus sensor would start looking for a star, it's like, oh, there's one. Oh, no, wait. Oh, wait, there's one.
That's a great excuse to cover up for the aliens trying to contact us. That's
there you go. And that's another episode. But
well, okay. So if you'll indulge me for a moment, so the Kepler pipeline wasn't quite ready to handle all the data as I explained, because just a bunch of things that happened that required the engineers' time before launch. So but that didn't change the time when we were required to release the first catalog of results. So we weren't quite ready, and at the time, a substantial fraction of exoplanet discoveries had been retracted. So the discipline had a lot of egg on its face because of the number of retractions that were coming out in the literature. I mean, it was like 20% or something like that. It was huge. Like you would see a planet, or you think you see a planet, and then you publish a paper, you become famous, somebody follows up a few months later, the thing gets retracted. And so we were worried that for a number of reasons. One is that we didn't want to have any mistakes in our catalog. We didn't want to have holes in the catalog that were filled with retractions. At the same time, you have an instrument that's designed to detect Earth-like planets orbiting around sun-like stars. And so there's a lot of motivation to find Earth-like planets orbiting around sun-like stars. So the issue that we confronted was, if we release the data before we can properly clean it up and remove the artifacts and things like that, then people might go in and see a planetary signal that's not real, make a discovery claim, have that claim retracted, and they would get all the fame and we would get all the consequences of having the retraction, because it came from Kepler data. It's not necessary. The public isn't generally going to be like, oh, it came from Kepler data, but was it a Kepler scientist that showed it?
Right.
And so we requested, and I helped actually draft the document. We requested to withhold information on about 400 target stars. And so it blew up with a bunch of conspiracy theorists that NASA builds a spacecraft to find Earth-like planets orbiting sun-like stars, and then they withhold the data last minute and keep us from learning the truth about. And anyway, so that was a fun episode. Of course, 8 months later, all the data were out, but it didn't go over very well with certain segments of the population.
But we know that the real thing you were trying to hide was the life you found on Proxima Centauri. But I digress. So your mission is going fine. Then a couple of reaction wheels give it up. And so who built the reaction wheels? I've been dying to know. The same people that built them for Hubble, or a different company?
That I don't know.
Okay. Because I think we should get a little, I know it's been a few years, but a little nasty letter writing campaign saying, hey, you guys, 4 years on your reaction wheels, give me a break here. Because it's a flywheel, right? That you use to torque the thing around to look at other stuff, so you're not using maneuvering fuel constantly.
Right.
But you lose a couple of them, and now it's like, oh, gee, what do we do with our big space telescope that can only maneuver on, I guess, one axis at that point, right?
It could go on 2. So it had one spare. It had 4 reaction wheels. So it could orient the spacecraft. It could keep it pointed in the right direction, but it couldn't prevent it from rotating around the axis that it was pointing along.
But the brilliant solution, this is what I wanted to talk about since we started this episode. You have this mission, it goes great. You're kind of out hubbling Hubble, at least in this topic area, obviously a very different instrument. So we're all excited about this, and then, it's not working anymore. Wait, I have an idea. Let's point it in a direction that the solar wind pushes against the solar panels in the spacecraft to keep it properly oriented, and we'll stare that way for a couple of years until we move it. And I thought that actually it's 85 days per target, but what a brilliant solution. So that's the story I want to hear, Dad.
Yeah. So when the reaction wheels failed, I mean, everyone's heads were down, like looking at the data, and only the mission managers and stuff like that, they kept saying, "Oh, this reaction wheel, there's a little bit of friction in it." And me and maybe there were some collaborators who were like some members of the science team who were alarmed by it, but I was like, "Yeah, it'll work out, no problem." So when it actually failed, I was like, "What? How did this happen?" And we had just at that point passed the senior review that gave us extended funding for 2 years. So every 2 years, there's a senior review of all the major programs, and the bigwigs at NASA decide which things to keep funding and which ones to retire. And so we just passed the senior review. We had funding for a bit longer, but then the spacecraft stopped working. And so very quickly, NASA sent out a solicitation. If we were to give you a $500 million photometer that works really well, but we just can't point it very well, what would you do with it? And so there were a bunch of proposals that were submitted back to NASA about where you should point it, and a lot of us, myself included, said we should still try to point it in the original Kepler field of view because there's a lot of science we can do on the targets that we already know about. But there was an engineer at Ball who was the one who thought, maybe because we can't steer it in 3 dimensions, but maybe we can use the solar wind to help balance it so that even though it's still going to have some corrections, like we'll fire the thrusters to correct the attitude of the spacecraft, it should be stable for longer than it would be stable if we were to point it somewhere else. And so Ball started running some tests to see how precisely they could keep the pointing by using the solar wind as a way of limiting the motion that the telescope would undergo. So once they found that they could get pointing almost as good as the original mission, and that the corrections that they had to make, so they would fire thrusters to just put it back in the right spot. When they found that they could get the corrections that they needed to make down to a small, like basically one cadence. So they would drop one data point it's every half an hour. So it'd be like they could do it within 1 hour. So they would only miss one piece of data and come back to it. So they demonstrated that they could do that. And that basically just drove the rest of the design of the K2 mission. So the K2 mission is the resurrected Kepler. So in NASA speak, a mission includes the flight segment, which is the spacecraft, and the ground segment, which is the operations and the data analysis. So when the reaction wheels failed, the Kepler mission ended. And then even though they used the spacecraft to still look for planets, it was a different program, and so it was a different mission. So they called it the K2 mission. The first person I ever heard calling it K2, it was actually our proposal that we were writing. And one of the guys that was an author on the proposal, he was a member of the science team as well. He kept calling it K2 because Kepler 2 was too many syllables. And when you're trying to get your ideas out fast, you want to cut down on the number of syllables you use. And so that was ultimately the name that stuck, like somehow worked its way through the system. But once they found that they could do the pointing with pretty high precision, then that just meant that was what you had to do, because why would you sacrifice data quality when you could really recover a lot of what you were capable of doing? And so the K2 mission, it looked in a different part of space. It would have to change its field of view every few months, but it still got really high quality data. And actually some of the systems that the K2 mission not necessarily found, but studied, are among the most important exoplanetary systems that we know of. So the best example, actually the 2 best examples, are everybody else's favorite. Well, okay, so my favorite is the WASP-47 system. So WASP-47, it was a planetary system discovered by a ground-based survey called the WASP survey, which is the Wide Angle Search for Planets. WASP-47 was a hot Jupiter, and the K2 observations of WASP-47 showed that it had nearby Earth-like planets, like Earth-sized planets, but it was not in Earth-sized orbits. They're like few-day orbits. But that was the first time we'd ever seen a hot Jupiter that had nearby Earth-sized companions. And a lot of my early research was on looking for nearby companions to hot Jupiters. And so WASP-47 is to me, that's the most important planetary system that has ever been discovered.
I was going to ask if you had,
So everybody else thinks that the TRAPPIST-1 system is the most important planetary system ever discovered. And that was also studied by the K2 mission.
Mm-hmm.
Okay, so Tariq has a really important question he wants to ask.
Well, I was going to ask if you had a favorite. By the way, K2 is amazing. Everyone loves a sequel, right? And K2 just hits it there. It's like K2, this time it's personal, or
yeah,
K2.
Well, it's better than Kepler Resurrection. Yeah, but ask the question in yellow.
Yeah, so I wanted to ask if you ever got to name one. You said that WASP-47 was your favorite, but did you get to name a planet? Is that something that you had hoped to do?
No. It wasn't. I mean, they're all catalog names, right? Kepler 5, Kepler 21, Kepler 32. So the catalog names aren't really that. Those were all chosen based upon what the order of the publication dates were, which actually changed depending upon. You could have two papers that would be submitted to different journals at the same time, or like one could be submitted before the other, but the review process would slow one down, and so which actually made it a little confusing because we always worked with the different planet candidates based on their candidate number. It's called the KOI number, the Kepler Object of Interest. And so we studied KOI 157, we studied KOI 70, we studied KOI 72, we studied KOI 377. These were all really important systems. We spent, in some cases a year almost, or like 6 months to a year studying each individual one, really getting to know its family and its neighbors and stuff. And then we publish it, and right before publication, that's when the Kepler number was assigned to it.
Oh.
And so it comes out in the literature as Kepler 10, but nobody knew what Kepler 10 was. Like none of the people who worked on it really knew what Kepler 10 was. It was just like that was the number that came out of the slot machine when you pulled the lever right before the publication. So it took me years. I mean, it really was like clear until the 2020s. Maybe it was during COVID when I finally, okay, maybe I should probably figure out what these are. But it took me years to separate in my head the KOI number, which is what I was familiar with the actual Kepler planet number, which was usually something that was assigned after I had stopped paying attention to the system anymore. So KOI 72 is Kepler 10, KOI 157 is Kepler 11, KOI 377 is Kepler 9.
But you can always say, "Oh, Kepler 9, I knew you when you were KOI," right?
Yeah. So you get to know like what they were like as a child, and then you can't forget it.
I guess I would close. You've got this groundbreaking research. All of these worlds are yours, Rod, right? from Kepler and K2.
All their base are belong to me.
I love it, man. That's the first meme I ever was like ahead of. I was so excited when that came out.
What is it?
All your base are belong to us. Oh yeah. Man, it's a whole thing. We'll talk
I'm
about
having
it.
A grandpa moment. Okay, let's do it.
You'll have to look that one up, and you'll use it yourself, right?
Okay.
Ask your son, Rod. Ask your son. But I'm curious about what's next. What is like the next step beyond Kepler, beyond what has been done now, to either confirm these 5,000 or these other thousands more candidates Kepler found, or to just go into the discoveries, the ones that are confirmed, and like learn more about them? Like, what does it look like? What's the air taste like? I don't know if we can even do that with what we've got now.
Let him
what's
answer.
The next step?
Let him answer.
So that is there's a few next steps. I think the main next step is going to be to study the individual planets that Kepler found. So Kepler, I say it's a discovery mission, meaning that it's designed to just identify things that are interesting to look at. It's to identify planets. It's not there to measure the properties of the atmosphere. It's not there to see what the weather looks like. It's just there to find planets. And so once you have them found, then you need to go back and study them in more detail. And so that's where like James Webb Space Telescope comes into being. Webb is not a discovery instrument in terms of like for exoplanets. In that it's not there to find new exoplanets. It's there to study planets that we already know are there. You wouldn't want to do a survey with the James Webb Space Telescope of like trying to find planets that hadn't been discovered yet, because it would be a huge waste of time on an extremely valuable instrument. So a lot of the field is shifting toward, now that we know that where these planets are, how do we study them? One of the things with the Kepler mission is that it looked in a single part of the sky for 4 years. And as a consequence, most of the stars that it finds, most of the planets that it finds are orbiting stars that are quite far away. Because if you want to have a large number of candidate stars in your survey and you're only looking in a single direction, most of your targets are going to be really distant. So following on the heels of Kepler was the TESS mission. TESS is an all-sky survey. So once Kepler launched, at the time that Kepler was designed, we thought, planets would be in 1-year orbits. And so there wouldn't be that many to find. And you had to stare at the same part of the sky for multiple years in order to find planets. Once Kepler started getting data and we saw, planets actually orbit their stars every 10 days, then that changes how you design your mission. So the first mission that followed on the heels of Kepler is TESS. And that one surveys the whole sky, looking for planets that orbit every 10 to 30 days. But because it's an all-sky survey, now all the stars are a lot closer. And so you can get the bright stars, and those are easier to follow up with. There's a European Space Agency mission called the Plato mission that's supposed to launch sometime in the near future. That's also a follow-on discovery mission that's going to look for planets. I think at the time it was all the rage to discover new planets, and it's certainly going to discover a lot of interesting systems, but it's not going to be as groundbreaking as Kepler was, just because Kepler broke the ground, and so it's not really what it's there for. And so the characterization of the exoplanets is going to be done with missions like the James Webb Space Telescope. I guess another area that things are going to open up is the Roman telescope. So that's the one where one of the alphabet agencies talked to NASA and said, hey, would you like to have a really nice mirror? Not that anyone would wonder, what would an intelligence agency be doing with a really nice mirror? Right. What planet is it looking at? So the mission that was developed from there, it started off as W first. It was kind of the shotgun wedding of a bunch of different things in the decadal survey.
Oh, what a sad story. Yeah.
And then, but it's about ready to launch, and it's going to be, as they say in the Northeast, wicked awesome. In that it's going to be comparable image quality to Hubble, but the size of the field of view is hundreds of times larger than the Hubble field of view. So it's a really capable instrument. And with that one, it's going to be, the data are going to be good enough that we should be able to see, look at planetary systems right as they form. So we can look at young star clusters and see the planets in those young star clusters, which you couldn't really do with Kepler because it would be too risky to do it with Kepler. But now with this one, we're hoping to be able to see like moons orbiting planets that are still, so we're looking at planets that are still warm. And so then you can see the transits of the moons in front of those planets, looking to see, are the planetary systems different when they're young? If you get a really young system, it hasn't had enough time to really relax the way that planetary systems are wont to do. So the early solar system didn't look at all like what it looks like today.
So, okay, so this is our big chance here. And your book, by the way, great cover, which is not always the case with university presses. Great title, which is not always the case with university presses. So you have a book out called Hidden in the Heavens with Princeton University Press. Tell us about it and make us want to buy it right now.
So it is, it's basically like an insider view of both the workings and the science from the Kepler mission. So it starts off with some of the mission design. It gives a little bit of my own history and how I stumbled into being one of the scientists on the mission. And it also, it talks about some of the discussions we had. Do we focus, should we focus it? Should we not focus it? What's going to happen when it goes into safe mode? What happens when this coronal mass ejection almost fries all the electronics in the device? So those kinds of things, like what did we argue about? And so there's some of that is in there. The discussions about where we should allocate resources. So there's a little bit of inner workings of a mission from kind of a young, naive, wide-eyed kid. And then there are several chapters that are devoted to the science that we learned from it. So this is both exoplanet science, how a comparison between the planets that we discovered with Kepler and how they compare to the solar system and how their histories are similar and how their histories are different. There was a lot of stellar astrophysics that was done with the Kepler Space Telescope. So looking at one of the things you can do with the Kepler data is measure the structure of the stars that you're seeing. And so there was a lot of stellar astrophysics that was done with Kepler that is also included in this. And then just kind of a retro, like now looking back in the mirror, what have we learned and how does that affect science going forward?
Excellent. Well, thank you so much for joining us today. And I want to thank everybody for joining us with Jason Steffen for episode 137 that we call Strange New Worlds. Jason, where's the best place for us to keep up with your activities and what's ahead for you?
So I do have a website, jasonhsteffen.com, that has kind of my updated research. I just put some new stuff up there yesterday because I'm supposed to be working on an NSF proposal and I didn't want to.
Okay.
And then you can follow me on Twitter. I'm Horizon Sci on Twitter. Although I don't know, people are often, it's really easy to be disappointed in people that you follow on Twitter. So maybe that,
okay.
But I do try to keep my stuff mundane and things like that. I'm not really big on social media. It brings out the worst in me. So
yeah, well, and it just gets boring after a while. And speaking of boring, Tariq, where can we find you inventing weird new names? Where can we find you? Let me get through it. Where can we find you inventing weird new names for full moons these days? There we go. Just had to get that in one bit.
Funny that you mention it, but
yeah.
Once again, another reminder that as we're recording this, it's the full moon of November. It's the beaver moon. It's also the last super moon of the year. Everyone go up and look at the moon tonight. It's going to be gorgeous. But you can. I went out
last night. Sorry to interrupt, but I went out last night because I had heard at the last minute on the radio of all places, hey, if you're in Southern California, you may see the space station pass in front of the moon. So I sat there with my binoculars for 15 minutes and then finally tuned back in. They said, oh, wasn't that great? And it's like, how did I miss that? So I guess I was just in the wrong location.
It takes like a bajillionth of a second to pass the face of the moon. It's really hard to see. So, but no, you'll find me at space.com as always, looking up at the moon for the full moon and maybe even outside on the lawn to see the Leonids this weekend as they peak, of course, on the Twitters at Tariq J. Malik. And this weekend is going to be a cleanup. I have to put away all the Halloween decorations. So, and it's like the middle
always
of November.
Lovely to learn about your private life and your last colonoscopy. And of course, you can find me at pilebooks.com or at astromagazine.com where I hang out. And please, if you will, consider picking up an issue of Ad Astra. You can get it from that very their website at astromagazine.com. And you can download an issue for free. Remember, you can drop us a line at TWiS at twit.tv. That's TWIS at twit.tv. We'll welcome your comments, suggestions, ideas, and jokes, lazy audience. Get with it. And, of course, new episodes of this podcast published every Friday on your favorite podcatcher and elsewhere. So make sure to subscribe, tell your friends, and give us reviews. Good ones only. I used to say anything, but now that we're almost 2 years old, let's get the good reviews in. You can get all the great programming with video streams and more on the Twit Network, ad-free on Club Twit, as well as some extras only available there that I won't go into detail about for Tariq's sake, for just $7 per month. And for a limited time, new subscribers, I didn't write this right. Basically, if you bring in a friend or refer somebody, you'll get either 2 weeks or a month for free. I'll have to ask Anthony. I know it's one of the two. You can follow the Twit Tech Podcast Network at Twit on Twitter and on Facebook at twit.tv and Instagram. Thank you very much. Jason, thank you. It's been a real pleasure. Fun talking
to you. My pleasure. It's good to meet you.
Likewise. We'll see everybody next week. Take care, everyone.